checked in early.
Hey everybody, we're live right now. So who do we have all here? Let me see. I might need to turn my volume up just a little bit. I might be far away from the mic. Hey, what's up, Ren? We got everything going good right now. What are the questions on the project, or where are people at? Hey Terry, good to see you here. Do you like the new intro? We got the Rick and Morty one. I made that for Project One, but we've been reusing it. Hey Julia, good to see you here. We got a bunch of people here. I think we have like 8 people watching. But if you have questions, feel free to ask about the project. Project is due tonight for extra credit. Love it. That's awesome. We could do an interview of Terry right here. Let's hop over to the interview screen. We'll go to the where is it? We've got the interview screen right here. We'll hop over. So we've got Julio in the background right now. We've got the light right there. So I was thinking about making some bumper music for my classes. That's awesome. Yeah, definitely do it. Make some bumper music. Make some fun stuff. We've got it's been working really well here, and I think the more we expand online teaching, the better. And I don't know, students have been really happy with this, and I know you guys are very inventive too. So let's keep it up. Let's keep pushing what we're doing forward. So I keep looking this way, so like I feel like I should look that way and say, hey to you guys, do we need to uniform stack our histograms? Uniform stacking is a very good idea. The project does not require it. And what you'll notice is once again, I always do things slightly different. So hopefully people watch most of these videos like they don't just skip to us. I mean, you should skip around the videos and find the parts because there are timestamps that we put below the videos. But let's go ahead and see something right here. I'm using Project One data for this. We're not doing Project One data. Hey, Abigail, good to see you. You do not have to uniform stack your histograms, but you will see something interesting when you uniform stack them. If I look at, this is going to be a similar idea right here. Hey, Julio, good to see you. I've still got your picture up in the background for the for the interview thing. So I was saying I should interview Terry. So you're just sorry. I could take out your picture if you want. So we've got tip amount, and then I'm gonna do by payment method. And here's where people will make an error. So people will see this right here, and it looks like the tips are about equal for both. But if we go to uniform stack, we might see some differences. So we're going to go to uniform scaling, and uniform scaling is going to put them on the same scale. And you see that there are more outliers here. They're on the same exact scale. Exactly. I'll put like a fun interview background on. So that way, every time I go to the interview background, it's just you're in every stream now. There we go. And so I do suggest uniform stacking them. Who can tell me one thing I'm missing right now for 1,000,000 points? Who can tell me one thing I'm missing on my histograms? One thing you should probably have on your histograms that I am missing on mine. Does anyone know? Terry knows. The count axis, you're right. Count axis. Wow, nice job, everybody. Here's a trick. If you hold Command or Control and you click the options here, and so I'm holding Control on my keyboard, and I'm going to click count axis, and it'll actually do it on both. Now, if you don't know how to do that trick, you can just go down to the other one and go to histogram options and go to count access. But by holding Command or Control, it does it on all of them. Good to see you, Alex and Sydney. So feel free to ask a question, but this is kind of what we're looking for right here, especially this, once again, is not your question, but these are stacked histograms. You don't have to put them on a uniform scale, but it can help. Maybe your distributions, kind of dropping some hints here, maybe your distributions will kind of look like something like one here and one here. And you can tell that these two have vastly different whats. What do these two have very different whats for the histograms? They have very different, they're pretty normally shaped. Yes, I like that. There's a lot you can do with the properties. I had my other jump set to do everything I wanted, and then I would do stuff, and then people would be like, how'd you do that? And I'm like, oh yeah, it's set to do it automatically for me. No, it's a pro and a con because it really helps if you're doing stuff, and then sometimes if you're teaching, you're like, oh, you have to click these buttons. But I have my other jump on my my personal PC set to do that. What is the key difference between these two histograms? Is it the shape of the histograms? Is it the shape of the histograms that are different? Is it the spread of the histograms that are different? We've got shape, something, and spread. What is the key difference between these two histograms? Are they different shapes? Center, Julia, you're right. These two have very different centers, and this goes to show an x-axis line. Yeah, truthfully, and here we'll give a key hint right here, is though you can do stacked like this. This is around I think 3,500, and this is around like 3,700. And so we're dropping some major hints today. I'm not actually making the actual graphic, but I'm kind of showing you. You know, it's this, and I want to drop some more hints on this because this is a major like review of what's going on with the project. I'm just gonna write it. I'm gonna do it. I'm gonna put the mean here. I think I might have confused people last class because I put a P and I was saying like I'm not doing the actual thing. So we're dropping some huge hints, but we're talking major hints about this. I'm not gonna tell you. I'll tell you the sign. It'll make more sense. Okay, major hints dropped right there. Like answers dropped. So if it talks about the engine, it would cost. No, it's saying that they're gonna pay like for the new machinery. So it's like saying that they will buy new machinery and they're gonna update their factory. So they're gonna update their factory and get these new machinery that will make the engines. So they're gonna buy equipment that will make engines, and they want to pay $100,000 for it. And so what you do have in this is you have the current machinery. So we'll put a C next to here for current, and we'll put an N next to here for new. So we've got the new and we've got the current. And then what's interesting is the hypothesized value is somewhere in here. So when you look at this, and do realize that these are distributions of single observations, the distribution of the mean would be tighter and more normal. Hint, hint, hints for your conditions there. So there's some hints on conditions when testing the means. The distribution of the mean will be tighter and more normal because we're trying to see if the distribution is normal. So there might be singular observations that meet our guidelines. Like up here in this distribution right here, let's do the highlighter. In the, really? There we go. In the current machines, we do have machines that meet and exceed the guideline of 3600. Does that make sense? And then for the new machines, we have machines that do not meet the guidelines. But are we interested? This goes back to the questions that we're doing in this chapter. Are we interested in one machine or the mean of these machines? Are we interested in one machine or the mean of these machines? What are we interested in? A singular machine meeting the guidelines or the mean of the machines? You're right, the mean of the machines. We want the mean of the machines to meet the guidelines. So there's truthfully this distribution we can't see in the background that's tighter and more normal. It'd be something like this right here. That's the distribution we're actually testing. We're testing the distribution of the mean of the machines. So you don't see this distribution that's tighter and more normal. You see the singular observations. And that's why someone might say, well, wait a minute, we have current machines that meet the guidelines and we have new machines that don't meet the guidelines. But we're saying on average, would the new machines meet the guideline? And the answer is going to be yes. The new machines do meet the guideline. But does everyone see right here, if you were to do a statistical test and you wanted to test greater than, well, what we would do is we'd be able to plot our line right here. And let's see. So when we test the value of 3600, we're going to test it. It'll be a little bit different. The mean would be set right here. So when you test it, you would actually make a distribution that has the value at the center. So let's do this. This graphic got very interesting. I can't draw a normal curve like that today. Okay, so when you look at this, if you have your hypothesized value at the center, because what would you expect to see if the hypothesized value is true? I wish I could extend it down a little bit. You would have here mu naught. Mu naught is this value. Mu naught is that value right there. Mu naught is 3600. Does that make sense to everybody? So if 3600 is true, what would you expect to see if you took a sample of your machines? If 3600 is the truth, what would you expect to see in a sample? If 3600 is true, what would you expect to see in a sample? If 3600 is the truth and you took a sample, what would you expect to see? It's a redundant question, so think about it. If 3600 is the truth and I took a sample, what would I expect to see? So just pretend 3600 is the truth. Like, let's say, you're right, Sam, you got it, 3600. So that's why we put the center of the distribution. This red distribution right here, I put the center of it at 3600. It's the null distribution. It's what we would expect given the null is true. If the null is true, I would expect this. So let's look at our results right here. We're going to change one of these arrows and put the arrow going upwards. So this arrow where we landed at the new machines is about right there. And the arrow where we landed on the current machines is over here. So when you think about this, let's do, these are two separate tests. I'm not doing kind of the does not equals test. I'm doing one test on the distribution, one test with the new and one test with the current. But think about this. If you were to land right here and did a greater than test, would your p-value be large or small? If you were to land right there with the current machines, which is where we landed, Actually, I got to put my arrow closer to where it's actually at. Here's the center of the distribution. There we go. It's close to the center. And if you were to land right there, would the p-value for the greater than test be large or small? Would the p-value be large or small for the greater than test? Would it be large or small? Does anyone know? It would be very, very what? I think it's a greater than test. Remember what you do for the greater than test. The greater than test, I'm pointing the wrong way because I'm mirrored. Greater than test is that way. Oh, hey, Bellamy. It'd be very large. It'd be very large because everyone, it'd be very large because we're doing a greater than test. I might have pointed the wrong way. We'd be doing a greater than test. We'd be doing the greater than test. So always remember, shade in the direction of the arrow. So you always shade in the direction of the arrow. So we always shade the way, and I got to point this way, I think, because I'm reversed. So we shade the direction of the arrow. And think about this. Your sample mean was under, this is where the sample mean is at. This is Y bar current. This is Y bar new machines. So does everyone understand that the sample mean for the current machines is below what we hypothesize? Oh, the arrow is pointing down. Oh yeah, because I'm just this is the kind of the mean of the. It's not right on the mean. The mean of the distribution is right about here. There we go. There's the mean of the distribution. So and then it would be right here, and then the p-value would be this right here. Does that make sense? And so I'm trying to do it like on the mean at the center of the distribution. And so that is for the current machines. And then the new machines, if you were to land right here and you were to plot, the p-value would be very small. Now this is a totally separate test. It's not a does not equals test. We're just testing a greater than alternative. And we're seeing, okay, we landed at this mean. And what is the probability of something as extreme or more extreme than this, given 3600 is true? And the probability of 3700 is what? Is the probability of 3700 a large or small probability? Is the probability of 3700 observing that sample mean a large or small probability? Is observing 3700 if 3600 is true likely or unlikely? And so look at the p-value right here. Is that probable or not probable? Is observing 3700 probable given 3600? This one is small, exactly. So this one is not likely. Something as extreme or more extreme than 3600 is not likely. So we'd be saying we reject the null. So we'd say I reject the null that 3600 is the truth. I have evidence that the true mean, we got to put in a green pen now. I have evidence that the true mean is above 3600. So I'd say I reject the null for the new machines. I have evidence that the new machines would have a mean above 3600. Yes, that's what I like to see. It makes sense. So this was a big way of doing kind of a talking about it. But it's like, what do we mean right here? What's going on? I guess I kind of did a more like, this has been one of the biggest questions I'd say on the project. We got the sports shirt on today. So I really wanted to go a little more in depth on it because I always want to make a video that kind of walks someone through it. Once again, no ads on these videos. Don't worry. And thank you for everyone who's watched some ads. We have officially made our first dollar. It took us 1 week. We made $1. So we'll make $52 a year. That might be enough for a small pizza party. But thank you to everyone. And hopefully some people have thrown some likes on some videos. Some people have put some comments. Keep liking the videos, commenting on the videos, checking out the ones. But yes, it really helps out the channel. And thank you guys so much. Like, that's awesome. I hope it picks up too, Julio. Like I'm happy I'm happy already. One, getting monetized was awesome, and two, everyone being so positive about it. No one's like, why'd you monetize? Why'd you do that? Everyone's like, cool, let's get the pizza parties. Let's get more tutoring. I think everyone understands that I'm not trying to get rich. I just want to do pizza parties and tutoring. So that'd be really fun. But I can always I think I'll send the analytics to the department and be like, yes, here's the money we've made, so they can see and be like, okay, you made $400 pizza party and tutoring. What other questions are there? Who has a homework question? Any sort of question? That was a good kind of 15-minute review or so of just kind of one of the big questions and looking at the different histograms right here and doing the statistical test on the means for it. Also, knowing your values is very important. Just a very quick review on the nulls and alternatives. Everyone should know how to write your null and alternative by now. Don't worry if you don't. We're going to practice real quick. Here's a very quick review on writing the last two problems on the project. You got it. There we go. Alex jumps in, and let's do the last two problems on the project. Okay. So here we go. The last two problems on the project are as follows. In research, people have to avoid type 1 and type 2 error. Given the alpha level is fixed, give one suggestion. So wait. Oh, sorry, Sam. Let me make you a mod, Sam. Uh, I don't know. I don't know why Streamlabs did that. Sam, your mod, and Alex, your mod. Okay. So Streamlabs is a thing that we use. You can always check your points. So in case someone were to come in here and say some crazy stuff, then Streamlabs will like time people out. No, you're fine, Sam. Streamlabs it's hyper reactive. I've put it to the highest like thing where Streamlabs will jump on whatever happens. So that way like nothing crazy happens during streams, but it will like time people out or it'll delete messages if it thinks something's bad, but it's on like it's oh, what kind of error did Streamlabs just make? Someone's got to tell me what kind of error did Streamlabs just make? What error did Streamlabs just make? Streamlabs just made this type of error. Who knows? So what would Streamlabs assume about? No, it is very Streamlabs. You gotta calm down. You're okay. Everything's all right. Type 1 error. Streamlabs just made a type 1 error. It made a false positive. You're right. So he's innocent. You're right. You're getting it. Streamlabs made a type 1 error. I have it set very high to type 1 errors because think about this. When you're in Streamlabs or when you're chatting here, we would assume that everything is like a good chat. Like every single chat you make is just you interacting with Brian in a good way. And then the alternative is that it's a bad chat and should be blocked. So we'll put here block. So it's going to either say that something's good and let it pass through, or it's going to block it. So let's think about what a type 1 error is and the consequences of it. So this is a really good way. We set this up. We made this plan earlier. You'd ask about the question, then we would do a fake like, oh, look, someone got their message blocked. Streamlabs made a type 1 error. So so what do we have here? The null is whenever you chat, the null is that what you say is just good, fine to go. Does that make sense? Everyone, when you chat, it just goes through, and then we don't stop it. Like if you did the reverse, you'd need evidence it is good before you let the chat go through. Like everything would be blocked and have to be cleared. But right now, the null is that it's a good chat and it goes through. Uh, yeah, so if I come up and saying all kinds of rude things and I don't get blocked, that's a type 2. Yep, that's a type 2. If you were to get away, because in a type 2, so here we'll do it right here. A type 2 would be the null is false. So remember, in a type 2, practice right here. In a type 2, the null is false and we fail to reject it. So if Julio is saying all kinds of bad things, rude things, and so the null is false, we should block what the person's saying. The null is false because it's false. In a type 2, the null is false. But we're going to fail to reject it. So when you fail to reject it, you would say it's good. Does that make sense? If you fail to reject the null, you're going to say what the person chatted is good. So in a type 2, the null is false. We should be blocking them because it's false that they're saying good things in the chat. We should block them, but we're going to fail to reject the null. You always have to look at it and say it. So then you ask, what is the consequences if Brian increases his type 2 errors? Well, the chat could be filled with a bunch of really rude things that we wouldn't want. So the consequences of a type 2 error is the chat is filled with a bunch of really rude things. What are the consequences? Would nerd do? I know exactly. What are the consequences of a type 1 error? What are the consequences of a type 1 error if Brian has a very high type 1 error rate? What are the consequences of a type 1 error? How would you explain that to someone who doesn't know statistics? Or you say, well, if Brian really has a high type 1 error rate, what would be the consequences of his type 1 error? What would be the consequences of his type 1 errors? Type 2 error is everyone can get away with saying really bad things in the chat. And I might have to manually delete stuff. I might have to manually be like, oh no. So Streamlabs with a high type 2 error rate, people are going to say a bunch of really rude things, and Streamlabs is just going to let it fly. Because remember, you let the null fly. You fail to reject the null. So you're just going to say, oh, it's good things, but the null is false. They're actually saying bad things in the chat. Or blockable things, we should say. What would be the type 1 consequences? Type 2 is people are saying a whole bunch of bad things in the chat. Students could get mad and stuff. Oh, Julio, that is exactly right. Imagine if every time you came to class, it just kept blocking everything you said, and every 5 minutes I'm like, oh, Julio, I'm sorry. Streamlabs is so crazy. Oops. Sam, I'm so sorry. Julia, everyone's getting blocked. Okay, wait, we're gonna have to fix this. Okay, we're starting class. Oh, wait, someone got blocked again. Okay, wait. You'd be like, what is going on? What is going on? So you have to decide which is worse, and that's what people have to do. They have to like move up and down their type 1 and type 2 error rate, because if you could do like all type 1 errors and you could just block everything. no one would ever be able to say a bad thing because you would block everything. So what controls your type 1 error rate? This is now where we get to the last part of the review on this concept. Type 1 error is your alpha. That's where we do our counting. We remember this way. This is how I remember it. We've got 1, 2, alpha, beta. And these are A's and B's, like alpha is A and beta is B. So then we go here plus, and we go here to minus. So 1, 2, A, B, plus, minus. And so it's not, I do think that a type 1 is usually considered a false positive. Type 2 is considered a false negative, at least the way I like to talk about it. Like, think about what we just said. We said that there was a type 1 error, which is a false positive, which I usually think is rejecting the true null, because you're saying you have evidence of something when you don't. So I always think of it as a false positive because you need evidence for the alternative, and evidence is a positive thing. So I've always made the case for it being a false positive when it's a type 1. But you could reverse it. There's ways, but I always like thinking about evidence for the alternative as being the positive evidence for the claim. So what we would say right here is that if we want to impact our type 2 error, so I think that's what we're talking about for one of these last two questions. If we want to impact our type 2 error, we have to realize what goes into type 2 error. Can anyone tell me one of the 3 things that go into type 2 error? Does anyone know one of the 3 things that goes into type 2 error? There are 3 things that go into type 2 error. What are one of the 3 things that go into type 2 error? Like, that control it. Like, if you change this, it'll change your type 2 error. So what is, and there's one that's directly like, type 2 error is beta. Remember, 1, 2, A, B. Type 1 is alpha, type 2 is beta. And I just gave away one of the hints at what one of the things that controls a type 2 error. Like, it impacts your type 2 error. Any ideas? We'll see what the chat thinks. I'll give away the answers here in just a moment, but this is your time to practice. Alpha, nice job, Julia, right there. 1,000,000 points. So we've got alpha, we've got sample size, and we've got effect size. And then you should know what all of these are right here. Don't worry, it's just practice right here. So we've got alpha, we've got sample size, we've got effect size. I think that's for a previous thing, actually. And then if these go up, beta goes down. And so beta's right here. And if beta goes down, it's behind my head. If beta goes down, power goes up. Power is the inverse of beta. It's everything but a type 2 error. Power is the ability to reject the false null. And if beta goes down, power goes up because they're inverse. Just look at the equation right here. That when you have beta, 1 minus beta is power. So if beta is 0.9, power is 0.1. If beta is 0.2, power is 0.8. So they're inverses of each other. Alpha and beta are not inverses. I love it. We haven't used that test question in a while, I don't think. But I love that because people usually think they are. People think like, oh, alpha, beta, they're inverses of each other. Or complements of each other. I said the right thing. They're not complements. They are inversely related. So you see that right here, that if alpha goes up, beta goes down. If beta goes up, or whatever, alpha directly impacts beta, but beta can be impacted by other things. So what are we talking about here? What does this all mean? Well, alpha is chosen by the user. Alpha is usually set to 0.05, and it's just your type 1 error rate. It's how willing you are to reject the null when it could be due to random chance. So when we set the alpha to 0.05, we're saying that, okay, 5% of the time, our results could occur by random chance, and we'll reject the null and say we have evidence. So literally, this thing I'm highlighting right now is the percent of time you are willing to reject the null and say you have evidence for the alternative when it could just be due to random chance. You got it, Abigail. We will do that here soon. We'll see if anyone else has project questions, and we'll hop to that. You got it. And then sample size. Sample size is just how big of a sample you take. When do you think you'd be easier able to figure out that? And here we'll do a different example today. Let's say you want to figure out who has the best pizza in Knoxville. So you go to Domino's and try a single slice of their pizza, and then you go to, let's say, Pizza Hut. Hard Knocks, because they're the best. You go to Hard Knocks Pizza, and you try one slice of their pizza. We got some votes for Bren's. So we're going to do Bren's versus Hard Knocks. So Kendrick, with Bren's versus Hard Knocks, do you think it'd be easier to tell who's better if you got one slice? Oscars, Braun, Stefan. Oh, cool. Yeah, like I used to have Oscars all the time and Stefanos. That's good stuff. Before quarantine. Do you think it'd be easier to tell who's better with one slice or maybe like 10 pizzas? I'm not saying you eat them all then, but maybe over a period of time you try 10 pizzas from these places, or you try one slice. So like, what do you think would be easier to tell which one's better? If you had one slice from each place, or if you had 10 pizzas over a period of time from these places? When would it be easier to tell which one's better? If you notice, what I'm changing here is the sample size. One slice is a very small sample, 10 pizzas over a period of time is a very large sample. Which of these times would it be easier to tell who's better? When would it be? Would it be easier to tell who's better if you try one slice? Imagine your friends, you'd be like, "Oh, I had one slice from them. They're horrible." And they'd be like, "What? You give them another shot." That's what they'd say to you. They'd be like, "What? Why? You need to. You might have made a false. You might have made a type 2 error. You might have made an error in your judgment." That's what all friends say. They say you might have made a type 2 error. That's what my friends say. They're my friends. But so I don't have friends because I talk too much stats. That's why. And so let's think about this right here. You ready? What we have right here is if we increase our sample size, which means we're going to eat more pizza because we like talking about pizza. So if we increase our sample size, we're less likely to make a type 2 error, which is when we make a false negative, which is when we would conclude there's no real difference between the pizza places. Hey, good to see you, Tracy and Julia. I see Julia's got a question too. So if you increase your sample size, hands for the project, if you increase your sample size, then you are more likely to reject the null when you should, which is this right here. You're more likely to reject the false null, which means if there is a difference between the pizza places, you're more likely to see that difference if you take a larger sample, which means you'll be less likely to make a type 2 error, which means you're more likely to reject the null when you should, this is the ability to reject the false null. And this is failing to reject a false null. That over there, I can't point to it. I go off the screen. I'm reaching to it now. That beta right there is failing to reject a false null, and this power is the ability to reject the false null. It's not making a type 2 error. Just look at it. Everything but, that's how we talk about probability, everything but making a type 2 error. So that is power right there. Effect size is how different the pizzas are. So, and I think we got some more questions right here. We got 3D, and we got another one from Sydney. Thank you, Sydney. Very good to have you. Sydney, why are you not a mod? I know. Names I see. Make sure I'm mod. Okay. And so effect size, I want you guys to tell me, do you think it'd be easier to tell? So we've got, I need Kendrick's help for this. Kendrick, would it be easier to tell which one of these is better? Hard Knocks versus Bren's. Hard Knocks is really good. Or let's say, Don was good too. Papa John's versus Bren's. Which of those would be easier to tell which makes better pizza? Hard Knocks versus Bren's, example one, or Papa John's versus Bren's. Which of those would be easier to tell where the pizza is better between the two like comparisons? If you notice, I'm highlighting effect size right here. Or we could do this. You know what's even better? Hard Knocks versus Bren's. You can do that one. Or you could do your friend who doesn't know how to cook versus Bren's. Yep. And so I made it even more extreme now because I said your friend who doesn't know how to cook versus Bren's pizza. So Kendrick, imagine you have Hard Knocks versus Bren's, and I know you might like Bren's a lot, but let's say Hard Knocks is pretty good too. So you're like, they're both pretty good. I still like Bren's, but they're both pretty good. That's a small effect size. So when you look at Hard Knocks versus Bren, we've got Hard Knocks right here, and we've got Bren's, and they're both pretty close in how good they are. Like they're kind of close. But then we compare Bren's, which is still here, to your friend who doesn't know how to cook. And so here's your friend down here, and this is a larger effect size. The effect size is the true difference between the null and the truth. It's the difference between the null and the truth. So you would assume that there's no difference. That's the null for two means. But it turns out your friend doesn't know how to cook, and it's pretty easy to observe that your friend's a pretty bad cook versus Bren's. But if you were to compare Hard Knocks versus Bren's, it's pretty close. Because maybe in truth, Hard Knocks and Bren's are pretty similar to you. Like you're like, they're both pretty good. You still might like Bren's more, but they're both pretty close. But the truth between your friend who doesn't know how to cook and Bren's is more extreme. I often use a sports example for this. We got sports on today. So I say, like, if I were to play Julio in baseball and we could see who hit the ball further. Yep. So what would have a bigger effect size? My brother and I playing baseball, hitting the ball, seeing who can hit it further, or Julio and Brian trying to hit the ball and see who can hit it further? Which of these would have a bigger effect size? Julio versus Brian, or Darren and Brian versus each other, that's my brother Darren. So Darren and Brian, who are brothers, playing baseball, seeing who hit the ball further, or Julio versus Brian, seeing who hit the ball further. Which of those would have the bigger effect size? Assuming your brother is not exactly he's not. He's not. He's pretty good. Julio would have the bigger effect size because effect size, The null would be that Julio and Brian are the same, which is totally laughable. And then the alternative would be that there is a difference. So an effect size here is the actual difference we see from the null. So when you think about this, you can think about a lot of different effect sizes. Imagine someone said to you, which has a bigger effect size? Let's say studying on your own for the MCAT, or paying for a Kaplan course for MCAT. And I'm not saying you should pay for Kaplan, but which do you think has a bigger effect size? Paying for Kaplan for the MCAT, or studying on your own for MCAT? Which do you think has a bigger effect size? Kaplan or studying on your own? Which would have a bigger effect size? And we could actually write out the null for this, and then we'll do the other project questions here. The null for this might be that the difference, we could do before and after. So the null might be that your mean after, and this is paired means, we don't do this one, minus your mean before is equal to 0, that there's no difference before and after, like after the tutoring or after studying on your own. And this would be, we might want to do a greater than, that you've actually improved your score. So if we're testing to see which has a bigger effect size, what do you think would have a bigger effect size on your MCAT scores? Going to Kaplan or studying on your own? What would have a bigger effect size? Like in truth, it has a bigger difference than 0. Because 0 is the null value. I'm saying that the difference between your after and your before score is 0, as in that it doesn't make a difference. But which of these do you think would have a bigger effect? Kaplan, you're right. So that's what effect size is. And you wouldn't know it, but it'd be easier to observe a bigger effect size. It'd be easier to observe that people who use Kaplan are probably doing better, probably due to the larger effect size we have, that they do a lot better than the people who study on their own. I'm not saying you should go to Kaplan, but a lot of these places, that's their job, to help people study for these tests. So they, if that's what they do, hopefully they do it well. So I know many people have had success with them. I mean, it's one of those things to consider if you're considering tests. And lots of people have had success without them. Just depends on, we could look at the variables. Like, that'd be interesting. Do a study on, But my brother, it's so funny. I know 2 people, and they actually break the mold. One of them went to Kaplan and it didn't do well, and one of them didn't and did extremely well. So it's reverse. So sorry, Darren. Sorry, Darren. He'll never watch these streams. The other person's even more awesome. They did even more awesome. Okay. But I like to use these examples right here because I think they make sense to students. So it depends on the teaching. You're right. Depends on the Kaplan you're at. Depends on the type of the student. Because if you are a self-motivated student who is doing your own work and has been successful, studying and using study guides and everything, you can do it all on your own. I never went to Kaplan. I did find, boom. Okay, there you go. I didn't do it. So I know another person too who's super awesome, and they didn't do it either. So we're both examples of not doing it. I didn't use Kaplan for the GRE. So you're right, Tracy, and then we'll head back to the other questions. This would fail because we're doing a person's after and before score. So this would not be independent means. This is condition 4. Really great review right there, Tracy. This is independent means, and these would not be independent of each other because it's someone's after and before score. So this would be what we call a paired t-test, and we don't do it in this class. It's not hard to do, but we just don't teach it anymore. We taught it back in like 2012. We taught it. It's a good test, but time, we don't have time to teach everything. Okay, so we have I think, where is it? Oh, Sydney. So the question, Sydney, are you still here? Rewind the tape, and I pretty much give away the answer. You're writing the null and alternative are the same for both machines. So you're just running 2 one-sample t-tests. You won't actually do this mathematics. But so Sydney's question, then there was another one previously too, way back in 2012 when we could go outside. So the one sample t-test is actually this right here. You will not solve this math by yourself. This is the one sample t-test, and you're not going to solve that. You're just going to write out a null and alternative and let JMP solve it for you. So the null and alternative are going to be, you need to know the symbol to put in position 1. And I give this away earlier, but this is a good review. I like to do things differently each time I do it. So maybe it resonates with somebody. Like, they see it a different way, and they're like, oh, I get it now. Which of these positions, hint the way I wrote it out, which of these positions, 1, 2, or 3, and there's 2 answers, will have the same thing in it when we put it in that position? Like, as soon as we put something in this position, it'll be the same for the null and the alternative. which of these positions, when you put something in that spot, it'll be the same for the null and the alternative. Like as soon as I put something in there, I'll write it for the alternative also. 1 and 3, you got it, Kendrick. Nice job. So I'll give away these answers. I already did in the video. If you put the mean here, which I suggest putting, you'll put the mean here. This is not the answer right now. The way I've written it, since I'm doing the mean, this is mu naught. So that I'm testing a hypothesized mean, but we need to know what the value of the hypothesized mean is. That's what we're actually going to put for this problem. And the value of the hypothesized mean is 3600 for this problem. We did this earlier, so I'm just doing it again. And now you know the null always has the what. I want to see it in chat. Who's got it? For position 2, the null always has the what sign. The null always has the what sign. The null always has the equal sign. You got it, Kendrick. Amazing work, Kendrick. The null has the equal sign, and then we want to do greater than. So you guys know the null always has the equal sign. Makes a lot of questions easy. The alternative can have these right here. Those are the possible values for the alternative, and then we simply pick the one we're going to use. And there we go. That's got it. And we're going to let jump do the work for us under the t-test. So we'll do analyze distribution test mean. So if I go back to my data in jump, this is not the actual project data, but to do this t-test, which is right here, so that t-test you see on the top of the screen can be done via, sorry, all of a sudden phlegm, sorry. Go to test mean, and you just put in a value that you want to test, such as like 5. Does everyone see how 5 is right close to the sample mean right here? Since 5 is very close to the sample mean, I've got a standard error that is not too large. The t-statistic is going to be like negative 0.1. I'm going to say it's going to be negative 0.13. Negative 0.11 if I round it. And that makes my p-value very large. I believe so for 3C. Let me look at what 3C says, Julia. I believe so. I believe so. 3C. Yep, right, the null alternative. Yep, you got it. Have we covered how to do 3D and E on the project yet? I don't know if I'm doing it right. Yeah. Here it is right here. We did that also earlier, Kendrick. Tell me if you have questions, but this right here, what I just did right here, is how to do 3D and E also. You need to make this graphic right here, and you're looking for the greater than alternative. So be careful. A lot of people get confused by these. Here, I'm going to make it look even crazier. Especially, so I'm doing something very similar. Tell me, ask your questions if you have them. I'm trying not to do the project a lot of times, but also do the project, like doing it but not doing it. So if I were to test the value of 4, that should give me a t-statistic of like positive 3.8. So let's test 6. So this should be negative 4-ish. Negative 4. Let's try it. There we go. It's negative 4. So we go right here. Thank you. Yes, this video will be totally available later. You're totally welcome. You got it. So what is my p-value for the greater than test? What is my p-value for the greater than test? Can anyone tell me the p-value for the greater than test? I tested to see if the average tip for card is greater than $6. I'm testing right now to see if the average tip for card is greater than $6. So just so I can make it clear, this fake thing that I'm doing right now. So you got it, Tracy. Nice work. This, which is not your project, I would go right here, and I can't wait to get the new mic stand because I always turn away from the mic. Eventually the mic will be like here, and I can kind of talk straight into it. And so that'll be way better. I've got a desk in front of me. I can't put the mic on it yet. So we'd have the mean is equal to $6, and the alternative that the mean is greater than $6. Okay, so that's our null, and that's our alternative. And let's go back to the output. So make sure you remember that since you are doing this right here, and we'll put the output on the same screen as it. So let's go screen grab this. We need to take this. Let's take this. If we're doing our test, don't worry. Someone's going to be like, oh, no, I already put the whole thing. You should be all right. But if we're doing our test, we really only want to show this because this is the only thing. Sure, we'll put it there. Really? Oh, my gosh. Of course. Okay, we can fix this. We can fix it. Let's see. No. Okay. Really? Okay. Let's try this. You ready? We're going to take, and can I not just grab everything? Oh my gosh, that is way too much. Oh, there we go. Well, okay. We'll put it up here. There we go. That one works. Okay. So let's go ahead and take a look at this right here and see what we have. I wanted to put it right below it. There we go. So here are our, I know I need an iPad. There we go. All the new Apple stuff looks so cool. Always does. So if you look at this, I really wanted to point out, I wanted to highlight on here the following, that we are doing the greater than test. So does everyone see? You should be able to notice now that this is the greater than alternative, which goes into this right here. This is the greater than alternative, and so it's right there with the greater than, and it has a very large p-value. Now, I've had people say to me, and I understand that the p-values here don't look very large, but here is where we landed. We landed right here with our sample mean. That is our y bar. Our y bar is right here. So the p-value is this right here. It's hard to see, but that's the p-value. The p-value is the greater than shading. You can do this in JMP, which it's not bad if you want to include a graphic like this. You can go to p-value animation, and you can go to the high side, and there's the p-value. So take a look at what we have right here. We'll put this over here, and if you look at this, the graphic I'm showing you right here is the same thing. I'm showing you that here's where we landed. I'm kind of doing the line. Hey, Jeff, good to see you. And the p-value is 1, which means, well, it's basically 1. You might say, well, it's 0.999994, but the p-value is basically 1, telling us that we do not reject the null. So always make that clear. When the p-value is very high, you let the null fly, and you don't reject the null, so you would not have evidence for the alternative. The one right here, let me hover over it. If you put this, you're totally fine. You can do this if you want. You could even, like, if you scrunch up, the numbers are going to look crazy. This is not a bad graphic to use. You can use it if you want. You are not required to use this graphic. This one right here does show the right p-value, but I've had people get confused and be like, wait a minute, the p-values look very small. It's just that JMP shades the smaller ones for you. JMP shades the two-sided and shades the low side, and it shows the smaller ones. So if our p-value is 1 for the null, we do not fail to reject. So since the p-value is high, just let the null fly. And if you let the null fly, you fail to reject. So you would not reject the null right here. So you would fail to reject the null. So you would not reject it. You either reject the null or you fail to reject the null. When the p-value is low, reject the null. The p-value is high, just let it fly. So you're going to not reject the null. And in this instance, this fake problem I made up right here, I would say that I do not reject the null. I do not have evidence that the tip that people are giving for, I think it was card, is on average greater than $6. I do not have evidence for the alternative that the tip that people give for card is greater than $6. Yep, and I would say that we don't have evidence for the alternative. That's a key thing right there. We failed to find evidence for the alternative that the tip for card is greater than $6. I do not reject the null that the mean for tip is equal to $6. The mean tip for card is equal to $6. I do not have evidence for the alternative. So it seems to me like we can't say that people tip more than $6 on average for cards. That's what we're getting at. We do not have evidence for this down here, because if the p-value is low, we'd have evidence for it. Hey, what's up? Yes, you will mention the new and the current machines. Definitely. Katie, great question right there. Definitely. But if my alternative was 1, would you reject? Yes. And then we got another question right here. If the alternative was 1, which let's do this right here, and Tracy says, I was watching a quick briefing on coronavirus somewhere, and the doctor used a lot of... Yes! Send me stuff on that. That's awesome. Yeah, like type 1 error. Maybe they mentioned type 1 error. Who knows? But these concepts are very big. Does everyone notice right here that this is a very, very large mean that's bigger than 6? And so the standard error is this. That's 2.76. That's 2/3. So we're going to get a t-statistic of about... My brain's slowing down. Wait. I should do it. It's going to be like 5, I think. 5 times that, 4. It's going to be like 4 something. Okay, cool. So let's go here to test mean. And let's type in 6, and let's do it. And my brain was way off. Oh, no, it's 4.5, 4.45. So here is the t-statistic for the other test. And if you notice here, this time I'm testing the mean of cash. So if you notice, the mean for cash is actually, let me grab it all. So here's the statistical test. I'm going to put it on the screen. And we're going to change up what we just did. This is very similar to your project. So if you notice here, I have to change this graphic a little bit. In this example, the current machine is the p-value is 1. Correct, Katie, you're right. For the current machines, you would fail to reject the null. For the new machines, for the current machines, you would fail to reject the null. For the new machines, you would reject the null. There we go. Okay. So now, it's almost perfect. If you notice right here, here is our observed mean. And can I erase? No, we just got to erase one more thing here. It's off the screen. Dang it. I think I have to send this to back. So, oh no, I can't erase that p-value stuff. That's gonna make it confusing. 2 seconds. I'm gonna try to erase that p-value stuff. Okay. You know what? Let's just do it again. Here we go. So what's going on right here? We have the same null and alternative for this. The null, this is Brian's made up question. The null is that the mean for tip is equal to $6. The alternative is that the mean for tip is greater than $6. That automatically means we need to look at this one right here. Please do not, here's the biggest thing, is don't just look for a p-value you want. Don't be like, we like low p-values, which that's arguable, but you want to look for the p-value that goes with the sign. So if mine is worded like, the p-value for the new machinery is equal to 0.001, which is less than 0.5, meaning it's statistically significant, but we should reject, meaning, and since it is statistically significant, we reject the null for the new machines having an engine life of this. Does that make sense right there, Jeff? So meaning it is statistically significant, thus we reject the null for the machines having an engine life of this. Correct. And then I would say we have, I don't want to say the full thing on here, but we have evidence for the alternative that the true mean life or true mean daily life of the engines. Does that make sense? So whenever you say I reject, you would say I reject this. I can't. Great job, Jeff and everybody. I reject. And then you would say I have evidence. So in this one, so you would say I reject the null that the true mean for tip is equal to $6 for cash. I have evidence for the alternative that the true mean tip for cash is greater than $6. Now, please make sure to look at the right thing right there. And then if you notice, here is the mean. So that is the mean right there. We're observing that line. And this right here is mu naught. So that value of 6 right there is mu naught, which is this. This is mu naught. This is y bar. I missed how you got test mean to go to t-test. Yes. So you click on there. You guys are awesome, Jeff and everybody and Tracy. I appreciate all the questions, you guys helping each other out. You go to here and you go to test mean. So you go right here. Yeah, just you go right here to the second arrow. So under the second arrow right here, and the project says use 3600. Bingo, you got it. Test mean. You're awesome, Jeff. And then you go to 3600, and then you click OK. And so, of course, 3600 is way off the scale on mine, so the t-statistic is absurdness. So if you notice, I tested 3600. So where is this red line at? The red line is still at 5, or 4.9722. What is the third condition for question 3? So remember, we have a bunch of different conditions. We have condition 1. I need to see in the chat. So I think Julia knows this already because she's only asking third condition, which is awesome. Because everyone knows condition 1 is, oh, you guys know it. Here it comes. It's random. Condition 1 is random. Wolves are cool. We got that right there. So condition 1 is random. So condition 2 is 10%, meaning we need to sample less. And good to see you, Tiffany and John. We need to sample less than 10%. Condition 2 is 10%. So kind of draw some stuff out right here. I know, right? I have people, I still have people yell at me, QQ, straight enough, no outliers, plot doesn't thicken. They usually don't say plot doesn't thicken. They're talking about conditions for correlation, not regression. So I say that, and I think it just inspires people when they see me to yell that. Because they're like, oh, that's what people yell at Brian. It cracks me up still. And I'm going to be really sad. I mean, I'm going to come back and still visit Knoxville, but when I'm in Texas teaching, but it still just cracks me up. It's just like every story I have, I'll never get. Yes, Tiffany. It's funny. My mom was telling me about this lady she saw a thing on years ago who taught school, and she would make them sing songs to remember things. And so, yep, my fiance and I are going to Texas. She's got a residency in anesthesiology for veterinary medicine, so she's going to be no. So I'll still be here, Kendrick and everybody. Oh no, I'll still be here. And so, where will you be in College Station? So, College Station, Texas, Texas A&M. She got in there for veterinary anesthesia, so she's gonna be super awesome. She already is, but even more awesome. But your grandparents, that's so cool. No, so we're excited. It's gonna be really fun, and I know she's so smart. It's like I don't know. It's so exciting. She's just doing all these interviews and like I don't know. Thank you so much. I'm excited. Yeah, the food I know. I went to this is a very quick story and then we'll do third condition right here. So I'll be teaching. So what you see right now is the start of it. UT's been so nice to help me out with I mean, I've got like really good monitors. I've got my tablet. I've got professional lighting. And so I've got all this really great stuff. I've got my new key light here. You guys can see this right here. And I bought the green screen myself because I was like, you can actually see the green of it when I do this. So I've got an actual green screen behind me. But I'll be setting up a studio in where we'll be living. And so it'll be really interesting because I'll basically just like get up and be like, okay, time to teach, which I kind of do right now, anyways. But Brian, if you love Taco Bell, oh, that sounds awesome. I don't. There's what is it, Taco Loco? Or we tried one place because where she's at right now. I think what is it called? It's like Taco Locos. So I know I love tacos. And here's the thing, I'm a huge fan of well, one Taste of Thai, but Soccer Taco here in Knoxville. Soccer Taco is so awesome. Try Soccer Taco when everything reopens. Go to Soccer Taco, support them. Amazing food at Soccer Taco. And the barbecue. Oh man, I gotta start walking again, getting exercise, I gotta make some room for all this Texas food. So have you been to Chivo? I think yeah, yes, Chivo's really good. Chivo's definitely like high end tacos. I like Chivo a lot. I really like the Gangnam style. That's the Korean barbecue one, the Gangnam style. And then I also really like what is another one? They've got one with goat cheese on it. Maybe the Gangnam style is goat cheese, but Shivo is really good. That is really good. The guac word. Oh man, that sounds awesome. Man, it sounds so good. Uh, we love Mexican food. My tutor turned it into my dog sitter. We went to taco soccer together. Oh, so good. No, we'll be in what's it called? College Station. College Station. I live in Texas and I always miss the food when I go there. Oh, that's so awesome, Haley. So, the limp brisket, that's what it is. You're right. Oh, that's so good. That's the one with the goat cheese. Yes. And there's like another one I get to. Oh, the duck one. That's really good. The I don't know. I can say that name, but you know which one. The duck one's so good. Okay. We know condition 1, we know condition 2. Now we have to get to condition 3. What do we do when we go to condition 3? What do we do before we get to condition 3? What do we do before we get to condition 3? We're back on track now. We always have our 2 minutes of fun or 3 minutes of fun. What do we do when we get to condition 3 right here? What do we do? Pause. You guys are right. So you have to ask yourself what kind of data you're dealing with. You pause. You say, okay, let me just take a break. Let me slow my brain down. Let me make sure. You're right. And for question 3, condition 3 is nearly normal. So we pause. We slow our mind down. We say, what kind of data are we dealing with? So if it's categorical, then it'll be, let's do a different color right here. We've got categorical, we've got quantitative, and then we've got double categorical. So we've got categorical, quantitative, and chi-square test of independence. So if it's categorical, it is success failure. If it's quantitative, it's nearly normal. And if it's categorical, it's count data. And let's do this. So, that T looks horrible right there. Okay. So there's a big review of conditions right here. A big review of conditions. I see some. Was wondering if you just using more screenshots to support our responses. Yeah. And you can always have me look over it to make sure it's right. I'll look over people's screenshots. So that's good. And we'll do the nearly normal next, Julia. We'll explain that. Could you give these questions we support the screenshot I'm referencing? Can you give your opinion? Yeah. So the biggest thing, and I'll mention that here in a moment, Josh, we'll do the conditions and we'll hop to these questions. Great questions. And so I want to point out the biggest thing right here. Take a look at this right here. This is for what two tests? When do we do nearly normal? What test do we do nearly normal for? A one sample this and a when do we use the nearly normal for a one sample this and a two sample t? When do we do the nearly normal? Who knows when we do the nearly normal? Who knows when we do the nearly normal? We have histograms. You're right. There'll be histograms. And so if we have histograms, no pie charts, because that'll be categorical. Categorical is pie charts. That'll be proportions. So histograms and box plots will indicate nearly normal, which we can then use it. You generally want histograms. Two sample t, you're right. This one right here is the two sample t. So if that's the two sample t, what's this one over here? This one right over here is a two sample t. This one would be a what? You're right, that quantitative categorical, when you have a quantitative y and a categorical x, that's a two-level categorical x. There's more you can do with it. One sample t, you're right. This is the two sample t and the one sample t. And this is the one proportion z test. So this is a one proportion z test I've highlighted. This is a one sample t test. Make sure I said that properly. One proportion z test. One sample t test. Two sample t test. Chi-squared test of independence. So does everyone understand the differences between which ones to use right here? So this is very important, knowing when to know which third condition to use. Just knowing which one to use can help you out on the test because the conditions change based on the type of data you have. What do I mean by C? I mean, it's a question like, do you own a cat? Which is categorical. That's a yes-no question. What do I mean by Q? It's a question like, how tall are you? What do I mean by QC? It's like the heights of people who own cats. The height is quantitative, and cats owning is yes-no. So the heights of people who own cats versus the heights of people who don't own cats, it's quantitative categorical. We have a quantitative y, we want to analyze heights, and then we're looking at a categorical x. So then we look right here, and we have categorical y and categorical x. And so we would have something like, do people own a cat? Do people own a dog? So you could look, are people who own cats more likely to own dogs? Might be. If you own animals, you own animals. So there's one last thing here I want to mention. Let's go right here. And let's do this and do two variables. So tell me, when will there be a fourth condition? There'll be a fourth condition for which one of these two combinations right here? Which one of these two combinations will have a fourth condition? Who can tell me? This is our quick review of this. We're going to take all the other questions. Which one of these will have a fourth condition? You can just put it shorthand for me. I'll know which test you're talking about. Which one of these will have a fourth condition? Does anyone know? CC, you're right. I've already got that highlighted. The chi-squared test of independence has a fourth condition. You are correct. And what is the other one that will have a fourth condition? So we've got chi-squared test of independence as a fourth condition. What's the other one? What is the other one that has a fourth condition? It has to have two variables in this class to have a fourth condition. Oh, thank you, Jacob. It's gonna. I think I want to do the. I might do like the Doctor Strange thing, QC. So I don't know. I'm like debating, like bring it down to like a goatee or something. So QC, you guys got it. You great job. So this one right here is independent means. And this one right here is, I can't think, it's expected. There we go. The expected cell count. Am I blocking that? Oh, good. Expected cell count greater than 5. So this is a big Cliff Notes version of all the conditions. Sorry, my handwriting is so horrible. We'll zoom out just a tiny bit right here. But there's a big Cliff Notes version of what's going on. And then someone wants to know how to check the nearly normal. That I think was the next question we had going, is how do we check the nearly normal? So make sure to review these. I've got another video going over this more in depth. So check it out. But here are all your conditions. It's pretty easy. Random, 10%. Then you pause and you say, what kind of data are we dealing with? And then you choose success failure if it's categorical, which means we need at least 10 successes and at least 10 failures. Nearly normal if there's quantitative, more on that in just a moment. And count data if it's categorical, which means it literally is categorical. It passes the condition by virtue of being that. And then the fourth condition exists when we have two variables, like quantitative categorical is a two variable thing, a bivariate relationship. So we want to see if the two means are independent. And then with count data, we want at least 5 expected cell counts. And we covered that lecture yesterday, talking about that. So independent means is with two variables for QC. Yes, and expected cell count greater than 5 is for this one right here. So expected cell count greater than 5 is for that, and this one is for this right here. I think you should join the COVID stash. That's too funny. That's too funny. No, there's no fourth condition for the project because we're not doing the two sample mean test. So there's no fourth condition for the project. This project is only doing the project is doing this one right here. The project's doing that one. So there's only three conditions. There's only three conditions. You'll only stop at nearly normal. So this is just a review for a great job. Great question right there, Jeff. So the question was next, and then we'll do some homework after we do a bunch of the projects. No, people want some chapter 19, so we will do that. And so the question was, how do we look at nearly normal? Nearly normal is a very complex condition. That's, I think, where people have trouble with it. So really, there's four ways to look at nearly normal. Let's review. Way number one is to just look at your histogram. So this is the look at your histogram method, which is worth mentioning. We shouldn't stop at this, but way number one is to simply look at it. If your histogram looks like this, do you think this is good or bad? If your histogram looks like this, is that good or bad? What do you guys think? The top graphic. Yep, that is going to be the good right there. That is going to be the good. So that's the good, and that's the bad. So if I saw the top graphic, I would say something like, my histogram is mostly unimodal and symmetric. This is good evidence that it is normal. So that is good evidence that the top one's normal. The bottom one is my histogram is very skewed to the right. This is evidence that it is not normal. So as everyone see, I'm kind of even using like a null alternative by saying my histogram up top is very normal. I don't have evidence of it being not normal. The histogram down below is very skewed to the right. Don't stop at that though. Don't stop at that. Here's another way of doing it. I don't suggest this one. You don't have to do way number 2 in the project or 3. I'm going to use way 1 and 4 really. So this is another way though, but we should kind of note in the background. Probably won't see it on the test because it's an older topic. We don't really, I highly doubt this will be on the test. This is a normal quantile plot. So normal quantile plot, when it looks good, will follow the straight line. This is an older topic, and the normal quantile plot will follow the straight line when it's good. So if our dots were to follow the straight line, that would be good. That means it's normal. It follows the normal, because the red line is what a normal is. But then you might get a normal quantile plot that's all kind of bent like this, and so this one would be a bad one. So this is the good, and this is the bad. So, oh, that's a check. We don't want a red check. We want a red X. There we go. There we go. And so basically, it's not, yep. And so it's not straight, so it's not going to be normal. So that graphic over there on the far side, and this is a normal quantile plot, so it's not going to pass the normal. So we would say that the bottom one does not pass the normal. Now, the next way is what we call a goodness of fit test. So the goodness of fit test has a p-value. So, but be very careful here, because this is where I'm going to say I'm going to go with way 1 and way 4. So I would not suggest way 3. Normal quantile plot is one way check normality, chapter 5. So, yep. Oh, you're right. Terry's right. It can be tools and techniques. It could show up. It could show up. It would be how do we check for normality, and it's a normal quantile plot. So that is a normal quantile plot right here. I'll make one really quick and jump. It is unlikely to show up, but it could. It could. So let's go right here and go to, where's my, there it is. Here's the quantile, what's quantile box plot? There's normal quantile blocks. So you notice this actually has a little bit of a bend to it. I actually would have thought it would have more. I think we're missing those outliers. Well, I would have thought that'd be more bent, but it's not. This one looks a little more normal, so let's look at it with the normal quantile plot. That one looks more bent? How is that? Oh, because it's got these more outliers right here, so it does kind of create that. So both of these, this one has a problem in here. So there is some non-normality to this. This is what I'm asking, is the graphic of the normal quantile plot something we should screenshot or just discuss in Flotext? Maybe screenshot it. It's maybe worth mentioning, but here's the biggest thing. So I'm going to change everything up when we get to condition number 4, and I'll explain why. So condition number 1 and 4 are going to be very important, and I will explain why condition 1 and 4 are very important. Or the way of checking 1 and 4. Way of checking number 3 is to look at the p-value. The p-value for this one is going to be very high, and the p-value for the second one is going to be very low. So, but once again, wait till I get way 4, and you'll see why everything all of a sudden changes. So the bottom one is a low p-value, and let's do this over here on jump. So here I'm going to do it over here. I'm going to go to continuous fit. Once again, you can always slow the pause down. Go to normal. And it fit the normal curve on here. It's all the way over here. So let's remove out some output, remove test, remove test, remove test, and then we're going to go to goodness of fit test. Where's goodness of fit? There it is. So if you notice the p-value here is low, so I'm going to reject that this is normal. But this goes back to something I said earlier. We are not looking at the parent distribution, we call it, the distribution of single observations. We are looking at the distribution of the mean. And what does the central limit theorem say about this? What does the central limit theorem say about the distribution of the mean for larger sample sizes? What does the central limit theorem say, even if our distribution is skewed, when we have larger sample sizes? The distribution of the mean will be more what? And will be more what? According to the central limit theorem, the distribution of the mean will be tighter, and another thing, it'll be tighter. You see, but this is skewed, right? The top thing here is skewed, but the distribution of the mean is tighter and more normal. This is why way number 4 is very important. This is kind of the nearly normal by way of large enough n. Because if you remember way back from earlier, we talked about we're not interested, I think we still have that graphic over here, we're not interested in these original distributions, we're interested in the distribution of the mean, which will be tighter and more normal. And then we're going to do some homework questions after this. I think we'll have covered pretty much a lot of the project again, which is awesome. So the distribution of the mean is tighter and more normal. Let's look at that again right here. Even though the original distribution I have is skewed, if my sample size is large enough, then my distribution of my mean will be nearly normal. So I'm covering really in depth right here. So the fourth way of knowing that your distribution is normal is the large enough n, so let's put a way right here, and we'll put large enough n right here. So lean large enough n. So we're interested in the distribution of the mean. So even if we have a skewed distribution, so if the distribution is normal, which you really can't see from one observation, then you only need at least 1 greater than or equal to 1. If your distribution is skewed, which we'll put a little bit of skew in here, so let's say your distribution is skewed, then you need greater than or equal to 25. And these numbers are a little bit subjective. There's higher order ways of doing it in statistics, so I've always liked 5, 25, 100, or 1, 25, 100. And am I blocking that? Good, I'm not blocking it. So the more skewed your distribution is, the water n needs to be. The more skewed your distribution is, the water n needs to be. The more skewed, because it's the large enough n condition. The more skewed your distribution is, the water n needs to be. I'll put it right here. Checks. So, check. Oh no, green check. And I hate that the book switches up numbers on these. The bigger, that's why it's called large enough n. So if your distribution is heavily skewed, if you have a sample size of 100, the distribution of the mean should be nearly normal. All of these distributions of means, this is a single observation, all these distributions, it's a horrible normal. And I guess we should do it in green because it's going to pass the condition. Make it very clear with the coloring. There we go. And the mean would be closer to here. There we go. Sure. Try to draw it as good as possible. These are distributions of the mean. We're not looking at the parent population. The parent population is the black distribution right there. The distribution of the mean is the green distribution, which you see via this applet right here. Here is the black distribution. Here is the green distribution, which I've overlaid. So 125, 100, that is the sample size we need. So what if I go here and I only do a sample size of 2? Will the distribution of the mean be nearly normal here with only a sample size of 2? With only a sample size of 2, will the distribution of the mean be nearly normal? Because we're going to say skewed. I know it looks heavily skewed, but we'll just call it skewed. Since it's skewed, we need a sample size of at least 25. So if I do the distribution of the mean of 2 observations, hey, Ashley, good to see you here, then this is still skewed. You see how this does not look nearly normal? But as we increase n, what do we get? A distribution that starts to look more and more normal. And what this distribution here is literally the mean of 25 observations. So now you notice that the distribution right here is 1 observation that is the mean of 25 observations. Here's another plot in the mean for 25 observations. And we keep doing this, and we build a distribution that's theoretical, that is the distribution of the mean of 25 observations. So this right here would pass the nearly normal because our distribution is skewed. We're going to say not heavily skewed. I know it looks heavily skewed, but it's just skewed. And a sample size of 25 would be large enough that the distribution of the mean will definitely be nearly normal. So think about this. Did your distributions... Does your distribution look normal or skewed or very skewed? So for those doing the question, I see is another one on the Excel output, I think. Does your distribution look normal, skewed, or very skewed? So good. Thank you for coming in here. I think I didn't say it to them. Katie, awesome. Let's do Katie's question next right here. Does your distribution look skewed, very skewed, or normal? What do you think for your distributions of engine life? Skewed, very skewed, or normal? It looks pretty what? By looking at it firstly, it looks pretty what? Does it look skewed, very skewed, or normal, your distribution of engine life? It looks pretty much what? How does it look? How does the engine life look? Does anyone know? The distribution of your engine life looks pretty what? Oh no. Well, it's not fine. I'm not streaming. I think we're still live, right? Here's a hint. Here is a hint right here. Does your distribution of engine life look normal? These are the original distributions. This is kind of what we did for a review of our stuff. When you tested engine life on your project, when you tested engine life on the project, did the distribution look normal, skewed, or very skewed? So when you made the jump output, we got to go to our jump output. Did your distributions look normal, skewed, or very skewed? So when you saw your engine life distributions, did they look normal, skewed, or very skewed? Yep. We will do that, John. We will do that here soon. I think we're going to do Katie's question, then we're going to do it. Yours was a little bit skewed. So if it was a little bit skewed, which of these numbers over here might apply? Because I would go to condition 1, then condition 4. If it's only a little bit skewed, and if you were to be really careful, which of these numbers might apply? If you're going to say it's a little bit skewed, like you say, it's a little bit skewed, which of these numbers would you want to meet for condition 4? 25. And that's being very, very like careful because you're being like, it's a little bit skewed. So I think we need at least a sample size of 25. So the distribution of the mean, did you meet the sample size of 25? Do you have at least 25 samples in your new and current machines? Do you have at least 25 samples in your new and current machines? You do. So that means you meet the condition. Remember, these right here, and I want to point, these right here, I want to put X's over them because these ways of checking are for the original distribution. When you're doing the distribution of the mean, you can look at the original distribution. It's not bad to look at, but we're really caring about, is the distribution of the mean nearly normal? If the original distribution is not normal, then it can still be normal by way of large enough n. But if you were to pass, like if you had this pass right here, you're good. If you pass that, that's fine, because if the original distribution is normal, and then the distribution of mean will just be more normal. Because remember, it only gets more normal. One last thing on that than Katie's question here. Because if we were to say that the original distribution is normal, then any distribution of the mean will be normal. So it doesn't matter what the sample size is for the mean, any distribution of the mean will be normal if the original distribution is normal. Does that make sense right here? If you were to pass for the original distribution and say that it's normal, I'm highlighting this one right here. If you were to say the original distribution is normal, then the distribution of means must be normal. Distribution of the mean of any sample size must be normal. So it would follow via the central limit theorem that it would only be more normal. So since it's normal, it would be normal. So that's a really good review of all the four ways of checking nearly normal right here. So hopefully that helped people out, and you got this diagram right here to help out with the 4 steps we kind of looked through. And then Katie had a question. It was on, I think, the Excel output. Well, let me see here. Katie's question, then we've got a bunch of homework. Can you go over part C in the Excel part of question 3? Is there an Excel part to question 3? I think that's 4, is it not? Where's project? Question 3. Are you talking about this one right here? Katie, are you talking about this question right here? So, and I think Julie might want this one too. So, and then we're probably gonna do some homework after this, or quizzes. We've covered a good bit of it. I hope this has helped people today. We've went in depth on stuff and we've covered it. Is this the one that you guys want? Pause for a second. So I think this is, unless someone corrects me. Okay. So the biggest thing is we need to know what's going on with our Excel output. Awesome, Jeff. Good stuff. So we're going to go and we're going to take our jump data right here. And what I'm going to do is I'm going to do it this way. I'm going to go Control A or Command A. I'm going to go Edit, Copy with column names. And then I'm going to go over to Excel. So we're going to open up Excel right here. So we've got Excel opened up. We jump in here to Excel and we paste the data. That's one way of getting it into Excel. You can just copy paste from jump. And now what we're going to do is, I do have some videos. Make sure you have Excel downloaded to your computer. I think the online version does not have the analysis tool pack. If you have issues, please contact us immediately. We'll try to walk you through how to do it. But I wasn't sure if we used a percent or number for the conference. Hopefully this will clear it up right here. And so now I already have the data analysis tool pack. You might not have this. If you do not have this currently on your computer, one, you need to have Excel downloaded to your computer. And two, I have a video going over how to do each one. You got it. We'll do 2B next. You got that. And let's go here. We want to go to descriptive statistics. We click OK. Now we're going to click the column we want to do. I'm just going to do age for the heck of it. Obviously, I'm doing a different data set right now, so I'm not doing your questions. Label in first row. I forgot that last time, and it said nope. And I was like, oh, I forgot to click label in first row because there's a label up there. That's why it's clicked. Summary statistics and confidence interval. Click OK, and we're good to go. Now here's the cleanup I do on it. I take this and I copy it down to an area where I can work on it. I'm going to delete this out. This is not things you have to do, but, you know, like, why not make it look nice? I don't want that there at all. Delete. There we go. I'm going to zoom in on this and make it look nicer. If you double click this right here, it'll expand to your selection. So let's put this more towards the center of the screen. So can we not go over more? There we go. And so I've expanded it simply by double clicking this right here. It auto expands to the length of the window. I'm going to go right here and I'm going to go to the borders under home. Where's my borders? And I'm going to put in full borders. I'm going to select these windows here, merge and center, full border that. And then I'm going to go here and I'm going to put in regular borders and then I'm going to put in full borders. Okay, so kind of makes the table easier to read, at least I think. This is the variable we're analyzing, so I'm going to change the color of this, make it like that. Here's my variables here. We're going to put in another color. You can pick any colors you want. And then here's the variables I really want someone to see. So the variables I really want people to see are these right here. These are the ones I'm going to call your attention to. So I'm like, those are the ones. Then we'll use, oh, we don't want to use that color. We'll use this right here. Cool. Pretty obvious which variables I'm calling out right here, that I've got the mean and I've got the margin of error. And so a lot of people wonder, how do you know that that's the margin of error? Well, the margin of error is basically 2 times the standard error. So this is kind of a quick trick. Now, don't times the standard error by 2 to get the margin of error, but if you basically take, this is the standard error right here, which is s over square root of n. If you take the standard error and times it by 2, if you have a large enough sample size, you are basically doing a 95% confidence interval. Because if you remember from back in the day, 68, 95, 99.7, but we don't have to estimate it. Don't do that. Do not times that by 2. I want to say this again. Do not times this by 2. I don't even want to write it. I was going to put a big X over it after I did. Don't times that by 2 because they've already done the mathematics for you right here, because this is the margin of error. That is the margin of error. And you might say, well, why is that not it times 2? Well, the t-statistic depends on the sample size. If the t-statistic, if we have a large degrees of freedom, then it is very close to 1.96, which is very close to 2. If we have a small amount of degrees of freedom, then the t and the z are vastly different. So if you remember, the z-score for a 95% confidence interval is 1.96. Subset, yes. Make sure you use your subset while you're doing this. Great question. Or you're asking, oh, wait, is this for R? Oh, yes. For 2B, can you tell me how to subset the data to get the current new machines in R? Yeah, let me do that real quick. I think I can put that in the chat. And then, so I think, was there another question on here? Let me do that for you real quick, Catherine. What is going on with that? And this right here is y bar. And then we would do plus or minus the margin of error. So Catherine, we'll do that question next for you right here. Does everyone understand how to create the interval right here from the Excel output? Does everyone understand how to create the interval from the Excel output? This is the interval from the Excel output. This is literally how to make it right there. Okay, so then I think the question was, how does this relate to a 95% confidence interval? So I want everyone to just round these numbers right here. We're going to take this number right here. We're going to play the pretend game and call it this. We're going to take this number right here and play the pretend game and call it this. Don't change your numbers. Don't do that. Please do not do that. So I want someone to tell me what my 95% confidence interval is, and we'll do Catherine's question next here. Can anyone tell me what my 95% confidence interval is right here? Can anyone tell me what my 95% confidence interval is? Goes from what to what? My 95% confidence interval goes from blank to blank. What would it be? Can anyone construct using this sample mean right here and this margin of error down there? Because this is the sample mean right here. That is the sample mean, and that is the margin of error. Who knows what the confidence interval would be constructing it? It would go from 30 to what? It would go from 30 to what? I need someone to tell me. People were saying yesterday, Brian, you don't know this stuff anymore. And I was like, I know. My students help me all the time. I don't know how to make the confidence roll. I think the lower bound of it is 30, but I don't know the upper bound. Who knows in the chat? If you're watching the video, make sure you're solving it right now. You should be able to solve this. I always encourage people to pause the video, and figure out this confidence roll. You should know it pretty quickly. Give another 10 seconds here, see if they know it. This confidence roll goes from 30 to million points on the line. 30 to 30. Someone was like, come on, Brian. They're watching the video right now. Like, come on, you know it's 30 to 33. Oh, no, I said it. Okay, it's 30 to 33 is my confidence roll. So when we look at the value of our confidence roll going from 30 to 33, so the interval goes from, how does your extra credit system work with the points? So at the end of the semester, when I do any sort of rounding on people's grades or like bumping up to the next grade level, it's at the very end, the amount of points you get. I look at everyone's grades, and so I'll explain this really, really quickly right here. I make a distribution of extra credit points, which I've got all different lines of extra credit this semester. Usually looks something like this right here, and then there's like crazy outliers. And what I do is I take and I put a line down, and I say this is max, and this is 0. So the max is up to 2 points on your final grade. So all these people here get max extra credit, because there's always like outliers. I don't want someone to be like, oh, they got so much, they ruined the scale. So everyone over here is scaled to this right here. And so you can see like the bump you get in your grade is dependent on how much extra credit you get. So at first, when I started teaching, I didn't have a really good way of figuring out whose grade to increase. And I would never, it's just people would be like, Brian, you need to get to the next grade level. And I'd be like, and it just got to me because I didn't know how to like increase grades. And then I came up with my extra credit system when I just like give out points in next semester. And you guys probably know this. I think we're just going to go straight Streamlabs, because Streamlabs tracks the points just like this. So you can look at your points in Streamlabs. The more you chat in the chat, the more points you get. Streamlabs updates the points. It controls it. It's 100% like total works system. I have 460 points, but every time you chat within 5 minutes or outside of 5 minutes, you get points. And so how do you keep track of these points? We have a sheet right now that people fill out. It's a little bit of the honor system. I trust people, but next semester we'll be going straight via Streamlabs, I think. So next semester it'll be really easy. 185, that's really awesome. Like over like 100, close to 200 is really good. So it shows that you've been here a lot, you've chatted a lot, Jeff. And at the end of the semester, I can literally pull it up and look at it, and I can see like how many points people have. And so it'll be 100% fair. It's just the more you've interacted. I know that's what I really like about Streamlabs. And so it's just like you just chat in the chat, and then boom, you get the points. And it's literally like, see, like Abigail, amazing job, Abigail. That's definitely like 600 is really high. The highest. We'll be doing this for 320 also. So if you're in here in the chat and you're chatting, all you have to do is just stay active, stay chatting, and it'll tell you your points. Like you can ask your points anytime. I can do like polls and stuff. There's all different things I can do via Streamlabs. Like I can literally do a poll in the chat. So I'll show you guys that real quick, and then we'll go back to doing questions. Yeah, we got enough time. And I'll answer Catherine's question. Let me see here. Streamlabs. Gets the dashboard up. Okay. Am I logged in? Hopefully I don't. Watch me mess everything up. Stream ends. Is it going to work? Okay. I am in Streamlabs. So one of the cool things I can do, and I'm trying to get better at this, I just had to get more practice. I've been making so many things. Okay, so we'll start this poll right here. So we've got, how do you guys like coffee? So right now I've started a poll on how do you like coffee. So the possible answers are cream and sugar, black, or coffee is gross. So you have to do ! vote, and then you have to do B, like you do this right here. Like I like cream and sugar, so I would do this right here. So that's my vote for cream and sugar. So go ahead and you can either do, oh, it's already showing my vote on here. So you can, we've got a vote for gross. Cream and sugar has been voted again. So we've got black coffee right there. So it takes actually a moment to tally all the votes. Oh, I'm seeing all the votes. Top of the morning. Top of the morning to you. So that's, what's his name? Jacksepticeye. Good stuff right there. Good stuff. Love all the YouTubers. So it's close. Gross and cream and sugar are kind of tied. We might need someone else. So what I'm going to do now is I'm going to close the poll and complete the poll. So I can do polls like this. Oh, is it not? There we go. Complete the poll. And so it should say, and so you don't have to trust me. You can trust Streamlabs. Cream and sugar was the most voted option. It had 50%. There was 3 votes cream and sugar and 2 votes gross and 1 vote black. But imagine if I have 100 students in the class, they can all be voting on stuff. So I could say, like, what should we do next? And I can have a poll open and just click the poll option, and I can poll you guys, and you just type that in right there and you do it. There's other things. There's games you can play. There's all these different things, but it's pretty cool. I'll blow. Oh, it would have been tied. It would no. It would have been 3-2-2. So I don't know if I can reopen it. Wait, can I reopen it? What happens if I reopen it? No, it's closed. So I closed the poll. Which question were we doing? Oh, we're doing the confidence interval one. Okay. So with the confidence interval, and then we're going to answer Catherine's question. Then we're going to do a homework question or two real quick because I have to go to a meeting at noon. So let's do, and thank you guys and gals so much for showing up. It's always fun. I miss office hours. How do you find the critical value for only having the confidence and degrees of freedom? Is that a homework question, Elliot? If that's a homework question, I can help you figure it out. We'll put that next after the chapter 719 question. Which homework question are you doing right there? And I might be able to help you figure it out. Tell me the start of the question, and I'll help you figure it out, Elliot. So, or Elias, sorry about that. I looked just briefly at it. Elias, is it? Hopefully I'm pronouncing that correctly. Here is a confidence interval, and here is a test. Here is a confidence interval. That was our 5 minutes of fun, as per usual. Here's our confidence interval, and here's our test. If I make a 95% confidence interval, then what is the related, we do have to one tomorrow, you are correct. What is the related alpha level of the two-tailed test? 95% confidence interval, what is the related alpha level of a two-tailed test? What is the related alpha level of a two-tailed test if we're doing a 95% confidence interval? This is, I think so, it's going to be 5%, 5% or 0.05 alpha. So 5%, we're going to have a 5% two-tailed test. Now, when you have something that lands outside of your confidence interval, would that land in the rejection region? So if I were to test, my previous interval was 30. This was a fake interval I just made. It was 30 through 33. So 30 through 33. So since my interval is 30 through 33, then if I were to test 34, that would land outside of my interval, which means would I reject that value or fail to reject that value? 34 is outside my interval. Would I reject 34 or fail to reject 34? I'd reject it. You're right. So I could reject 34. If it's outside of a 95% confidence interval, I can reject 34 on a two-tailed test with 5% alpha. So doing a confidence interval is just like doing a two-tailed test. Anything inside the confidence interval cannot be rejected. Anything outside the interval can be rejected at whatever the 1 minus confidence level is. Confidence level here is 95. Alpha would then be 0.05 on the respective two-tailed test. If you notice how they are complements of each other, and they can use to do the same idea. So if you have your inside and your outside, it would add to 100%. Does this help with this concept? Does it make more sense that anything inside the interval, like if I said, do you think the age is 32, the average age is 32, you'd be like, well, yeah, that's inside my interval, and I would not reject it. So when it's exactly, when it is a 90% confidence interval, it would be a two-tailed test with 10% alpha. So if we were to do a 90% confidence interval, if this was theoretically that, it would be a 10% alpha or 0.10 alpha. So that's got it right there. I hope that makes more sense, but good concept right there that test and confidence interval are analogous, that you can use a test to do a confidence, or you can do a confidence interval to do a test, or you can tell if something is in a confidence interval by doing a test. So they are analogous. You're welcome. Catherine asked a great question about R. Let's hop into R. We're going to open up some R right here. I think it was how do you, and then we've got Elias has a question. And I think there was a chapter 19 question. We might do Elias's first if the other person's not here. And so get ready to ask questions, and thank you so much. Catherine asked, where is it? Okay. For 2B, can you tell me how to make the subset to get the data for the current and the new machines? Yes. Okay. So what we want to do right now, or you already have your subset. Catherine, do you already have your subset of your data? Have you already taken your random sample of your data? Have you already taken a random sample of your data? This is for 201. One of the students, I'm always proud, is using R because they want to do the whole project, and I like that. I'm always encouraging if a student wants to learn a programming language. So then they said, let's do it in R, and I said, let's do it in R. So what you want to do is for 2B, you want to make the what do we call it? The distributions of it. There's a few ways to do this. I'm gonna do it with a different data set right here, and I'll put the code in the chat. I'm going to open up a data set right here, and I'm just going to do something analogous to this. So what I'm going to do is I'm going to look at survey 10, which has males and females. So survey 10 just has males and females in it, and then I'm going to use this to use it like it's new and current machines. So what I'm going to do is I'm going to have survey 10, and I'm going to have heights of males and females. So does this make sense? Like this right here is analogous to, oh, we're not doing heights, we're just doing gender. So it's just one variable. So this is analogous to the safe and the fail. Okay, then I see. Cool. And then we want to do something that's another 2-level variable. We're going to do like left and right-handed. So I'm only going to use left and right-handed. So this is handedness. So handedness does have ambidextrous, but I'm going to ignore ambidextrous. No. Thank you very much. I appreciate that. There's people I know things I know and I don't know things I don't know, which I'm sure that's true for everybody. But so we're going to go right here and we're going to use right and left-handed. So this is going to be like your new and current machines. So this is analogous to the new and current machines. Does that make sense? Like these are the analogous things you're doing. I've got a categorical variable and a categorical variable. So we've got two things right here. We've got one variable that is categorical, like your success, your safe and fail, and we've got another variable that is categorical, like your new and current machines. So what we have to do is here we have to use the subset function, like you were saying, and I would do the following. I would call this, let's call this right, which will be like your new, and you go to subset, and then we put in our data frame. First argument is data frame, and then we put here what we want to subset by, which is handedness, equals right. So if you notice right here, and then we go left, and if you notice we have a data set that is just left-handed people, we can confirm this by going over here to handedness and seeing that all the people, there it is, all the people in my left data frame are left-handed, all the people in my right data frame are going to be now right-handed. We could confirm this with other ways, but I know the code did it, but I mean, like, are you sure it's all of them? So I've now made a subset of these individuals right here, and from here we can just do the graphics. Like, you can make bar charts for this. Like, it's really cool because you can just go here to plot. It should just make a bar chart, or you can use ggplot because ggplot's awesome. And we can just go here to plot, go to survey 10, $, and go to we're plotting gender right here. And so there is a distribution right there, a very simple distribution. And we could add the counts to it and stuff, but there is a distribution right there. And then you just go right here. Oh, we did survey 10. We want to go to right. I want to go to our subsets. So there's the right-handed subset, and there's the left-handed subset. And is it param-flow? No, is it options? Oh, I always forget this. I gotta cheat and look it up. I lost my genius status. I lost it. It's like options param flow or something. Side by side graphics in our studio. Oh, I just saw it. I shouldn't have went away from that. No, that's not it. It's param flow. It's something like that. I know it when I see it. Oh, there it is. Par. There it is. There it is. I got it now. Okay. Well, someone's saying it's not working. They've got an error with it, so I shouldn't take their code there. Oh, there we go. So we put them side by side. Now we need to clean this up. There's a difference. I need to be careful here. This is not properly labeled, but there it is. It's parameters mfro. So I should learn what that's an abbreviation for. It'll help me remember it when I have to know the code. You know, you can always look up codes. If you know what to Google, you can really find your code. But now I've made side by side box plots, and I really should label these things. You know, sometimes I'll go in and I'll use Photoshop to edit a graphic if I can't get it to work in R. It's always better if you kind of know the codes for it, though. So right-handed is on the left. Oh, no. Let's see, that makes sense. Okay, so then we'll go here. We'll reset the param flow. And so the first time it puts it, there it goes. And then we go right here. There we go. There we go. It's good to make sure. And now we've got the left-handed on the left and the right-handed on the right. And the param flow controls this right here. So you could do something like this, and then you could do like three bar plots right there. So this is why I like what you can do with code, is because you can control every little thing. Like you could do something ridiculous like this right here, and we'll highlight this code, and then we'll do this. So you can do whatever ridiculous thing you want. If I expand the plot, it won't look so crazy, but you can make Yeah, so just knowing these options right here and what you can do, and you could go right here. We'll just do, oh wait, we'll do this. This is my last little trick. Last trick. Oh, it's super cool. I'd know even more of these, but so it should be, okay, cool. We should get what I want right here. Oh, oh, I know what I did. Forgot my hashtag. There we go. There we go. So now we got some nice. Do you use SigmaPlot for any classes as opposed to R or along with R? What is SigmaPlot? Send me information on that, Sarah. Sarah, I'm highly interested in what SigmaPlot is. I have not heard of that. Tableau is, very popular for graphical visualizations. I know. So what I did, I used hexadecimal color coding right here. If you're wondering how I got this right here, but this is hexadecimal color coding, so you can choose your color more finely using this right here, because there's actually 16 combinations of red, 16 combinations of green, and 16 combinations of blue. Does everyone see how I had FF0000? This is saying for this first one completely red. This is saying for the second one completely green, and this is saying for the next one completely blue. So you could turn up the green here a little bit and do this, or there we go, there's that color. So that is red green. So red green makes those colors right there, and we could redo this right here. So you could turn up, if you make purple, you think purple is red and blue. So we should be able to get a purple if we do some red and blue together. So now when I redo this, the first one should be a little bit purplish. That should be kind of purple. There we go. So purple is red and blue. I know, it's so fun. Nissan uses Tableau. I'm not shocked. Tableau is a very good software to use. And just knowing how code works and all this stuff, you know what's so cool about this? There's 16 different combinations of letters / numbers, because it's hexadecimal. That's 16 combinations. Oh, that's the one you want me to try right there? What is that is that actual purple? So that looks to be a lot of, that's red and green. Is that, and I should know UT's orange color code off the top of my head. I've put it into here so many times. Okay, so what color code is this? Oh, that's close to UT orange, it looks like. What is UT orange? It's FF, I think it's FF1900 or something. You can actually, that's, but I dispute it. I will tell you why. There is a branding site, branding UTK color codes. There's a branding site for UTK, and it's UTK brand. So I'll bring it down right here, and there it is, 82. Is that what? So they're saying it's this right here. This is the UTK branding. So here we'll compare. You ready? We're gonna do a comparison. So that's the UTK branding site. So here's the two. We're gonna compare. Oh no, what did I click? Oh, look at that. This is, our eyes probably cannot detect this, but according at least, I mean, this is literally, these two colors are different. So these two colors, I do see it. This one's a little like, there's a small difference. So we've got the UT branding site, and then this right here, which you know what we should do? We should put it to a vote. No, we should have people vote which one is the true UT orange. Can anyone else see the difference in these? I know it's slightly, there's such a small difference in these right here, but that's the cool thing about hexadecimal color coding. Yeah, I knew it when I see it, FF8200. I know it when I see it. I was like, it's close. My computer doesn't see it. Here's the thing, Tracy. There are this many combinations of colors. There's 16, there's almost 17 million different colors you can make with hexadecimal color coding. Imagine a crayon box with 17 million different crayons, and that's what hexadecimal color coding is. 17 million different crayons. There we go. I like that, Haley, right there. Awesome. We gotta do some homework assignments now. So I really like coding. If you guys can't tell, it's so much fun. It just expands your mind. Someone's like, my crayon box has 100 crayons. Someone's like, my crayon box has 500 crayons. Like, my crayon box has 17 million crayons. Well, I'm at 16.7 million. But I've got a lot of options right here. Like, you'll never see the difference if you were to go here and do, like, our eyes cannot tell that difference. No, I can't imagine someone be able to see that difference. You're welcome, Catherine. Remember to email me those questions. Hey, Joel, I think we had a question from, let's see, Elias had it. I think it was Elias. How do you find the critical value only having the confidence in the degrees of freedom? So, Elias, you should have Did you just compute? Oh no, I didn't. I didn't do it in my head. I did it on R. Oh, I wish I could do it in my head. I think I've seen it enough that I know it's like 16.7 million. But I typed it in here to the code, so I typed it in, and it'll solve it for you because you can just type in whatever you want right here, and it'll tell you the answer to it or like that. That's the cool thing about R. Also, it's a very very quick and easy to use calculator. So no, I can't do that in my head. You guys give me too much credit. 16 times 16 is 256, I believe. I know that one because I've memorized a lot of the common squares. Yeah, 256. So this is a very very common one. I'm not gonna. Okay, we'll stop. And so let's go and open up. Okay, so we're gonna go and do. I think we have time for 2 homework questions. So let's get those done, and let's do some homework questions. A lot of good fun this morning. Thank you everybody. You guys always make it fun in here. Um, it's like old office hours again, where we get some work done, we have some fun. So we did a great job this morning. So I hope you guys had some fun too. It is always fun in office hours. Let's check out the questions right here. Let's go to. I think Elias, if you're here, how does your chapter 17 question? That's awesome, Haley. I'm so glad you guys like it. Like that's what I want these streams to be like, kind of social, kind of relaxing. You know, we're all in quarantine, so I appreciate it. Elias, which one are you working on chapter 17? And I do have they are in other videos because I will have to go here soon because I have a meeting at noon. I won't go yet. I'll literally leave right at noon basically for the meeting. Which one are you working, Elias? It is good. It's pretty crazy. It's I don't know. I'm lucky that I have this because I think I'd be going crazy if I didn't. And I like this a lot better. It's I don't know. It's actually I feel like I'm talking to you guys when I actually see the chat. Zoom, I don't know. I think everyone's zoomed out maybe. I got zoomed out a while ago. I got zoomed out before we started using Zoom. Sorry, Zoom. I mean, no, I think it's excellent. I'm really glad everyone's using it, but I to me this feels like an actual it always has felt like it's real to me with this. Like I don't know. It's I don't know. I like it. Yeah, it's really nice to be able to see the questions. I think it's a lot bigger, it's a lot easier to read. You know, it's a lot easier to navigate and stuff like that, I think. So I think it's got a lot of pros. So I kind of invented this method too. Other people had thought of it, but pioneered it. Pioneered it, I would say. Like I was one of the people and recorded, yeah. And we'll see if Elias has questions or there was another question on chapter 19. So if anyone has a chapter 19 or 17, I will do that now. If you just put the star of the question, I'll find it and I'll do chapter 19 or 17. I want to hunt down maybe the one Elias was doing. I want to make sure we're doing the right one. You can put me on double speed. You can go to 1.5 speed. It's on YouTube. You can put comments below it. Like the video. Chapter 19, a lot of it is best done in jump. But I will say this. Okay, let me do this also. Tracy, do you have a TI calculator, Tracy? Do you have a TI calculator? Da, 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 da. Where is my TI calculator videos? Oh, they took the ads. No, I'm just kidding. Chi-squared. Oh, got a Grammarly ad. So, Tracy, do you have a TI calculator? Awesome. My question is one with root A and root B. Cool. We're going to do that here just in a second. Let's do this. Oh my gosh. What is going on? Okay, let me skip this ad. Okay, so Tracy and everybody with a TI calculator, here is one of the best ways to solve chapter 19. So this video right here, good, it's logged out again. This video right here is one of the best ways to solve chapter 19. I'm going to try to open it in a new tab right here. There to do it. Should go straight to it. Awesome. So this is how to solve the chi-square test of independence on the TI calculator. It's super awesome, really helpful. And do we include the total column when using jump? Like, do we stack the columns with the others? Which one are you talking about, John? I'll look back on that. We're gonna do Elias's question. Thank you, Elias, for waiting. Then we're gonna do the other questions here. Elias is wondering about the root A and root B question. Here we are right here with root A and root B. And so, Elias, for this question, we need to mark all the notation. So for this question right here, we need to mark all of our notation. Let's go in here, and we've got it ready to go. So the first thing we're always going to do is we're going to mark all of our notations. Wonder what to use. Oh, you'll use 3600, Elizabeth. You'll use 3600, Elizabeth. so where's my thing? Cool, losing my mind. And let's go here and let's mark our notation. We have that he rides each route 20 days. We've got a standard deviation. We've got a mean. We've got a standard deviation. We've got a mean. We now have our notation marked. So let's go in here and let's put here that this here is N1 and it is N2 because he's going to ride each route that amount of times. Now technically what we should do is we should use the notation they use, that this is NB and this is NA. This is going to be the standard deviation of B, and this is going to be the standard deviation of A. This is going to be the mean of route B. This is going to be the mean of route A. Mark your notation. Know your notation. We have the average time it takes to ride route A, the average time it takes to ride route B. We have the standard deviation, which is the variation, just like higher standard deviation means there's more differences in his times. They're more spread out. Lower standard deviation means his times are closer to the mean. Like here's a large standard deviation, and here is a small standard deviation. Standard deviation literally controls the spread from the mean. So the more standard deviation, the more spread. Smaller standard deviation, tighter distribution. Standard deviation is standard deviation from the mean of the data. So we see this all right here. With everything, I think we have everything written still on here. Awesome. We're going to use the equation. We're making a const interval, so we need y bar b minus y bar a. Now you might wonder, why is it y bar b minus y bar a? A lot of output uses the, hey Sydney, good to see you, uses the second alphabetical first, and apparently they did that when they wrote their question. It's just the way the question is written that it asks us to solve for y bar b minus y bar a. Now I know it's saying the true difference right here, but when you do the formula will use the sample distance. We might be able to, Oliver, we might be able to. I'll see later today if we could do it. I'll show up, and if he'll show up, we could do that. Oh wait, we're using A and B. And so I think we're right about to your question right here. Okay, so from here, it would just be plugging in the values. Does this make sense that you would just, I think we can do it, Tracy. I think we'll probably do it. So from here, we'll just plug in the values. There's the formula right there. I have class this morning, so oh, that's no worries. No worries, Elizabeth. We would plug in the values. Does everyone understand how you'll plug in the values? But here's where people always ask, how do you get this? What do I need to find to get this right here? Someone tell me in the chat, help me out. Brian, what do you need to find to get this t right here? To get that t, I have to use the what? I have to go and find the what to get that t. What would I go and find to get that t? I'm going to go to the 2 sample t degrees of freedom calculator. So hopefully people put that in the chat right here. 2 sample t degrees of freedom calculator, or degrees of freedom. You are right, Sarah. Nice job. So we're going to find the degrees of freedom for this. Great job right there. Don't worry, it's just practice. And then we have 2, 4, and 20. So I'll explain why I'm picking these numbers. Is that we have sample sizes of 20, remember I marked that, and a standard deviation of 2 and a standard deviation of 4. This tells me the degrees of freedom. So now that I know the degrees of freedom, I now have to go to the t distribution. So now that I know the degrees of freedom, I'm going to go back over here and go to stat distributions t. So let's go ahead and put this. I think I put the other distribution in there. Yep, so that's in the chat. And then we have here stat distributions t. Okay, so the first link I put in the chat is the 2 sample t degrees of freedom calculator. It's going to tell me how many degrees of freedom my t has. And so then I go back to the t distribution, and I have to put in the degrees of freedom. Now I choose this one because I'm going to make, I think, a 95% confidence interval. So this shows the 95% confidence interval that I am making. If you notice right here, we get a 95% confidence interval, which is going to be the middle plotted 95%, and I get a t-score of 2.052. So I think this is what Elias was asking about, is how do we get this value right here, and this value would be 2.052. From here, we're just going to plug in the values. Here's the 2 means, so we need to take the mean for B minus the mean for A, and then we take this one right here, and it's standard deviation squared This is 2 squared. This is 4 squared. 20, 20. And so that's, well, we can do this. Okay, I think I've got it. I think I've got it. I'm taking a guess at this. I'm doing it. I'm doing it. We're taking a guess. Okay. So wants 2 decimals. Okay, cool. Makes my life easier. Should the man believe that the 5-minute claim, 5 minutes in the interval? Yes, you should believe it because the interval contains 5 minutes. I think I've done this proper. Let's check the answer. Oh, I got the interval wrong, it looks like. Dang it. Okay, let's fix it. I was trying to do it in my head. Let's check. Okay. So I'm thinking. Let's make sure everything's right. Well, I guess. Did I not do it correctly? Let's check. Okay. So 2 squared is 4. That's obvious. That's what I was doing in my head. Plus 4 squared is going to be, and I'm making sure all my numbers are correct. 53. There we go. Hopefully. And then, so we go right here, and 20, it's going to be 2 squared, 20, oh my gosh. This is going to be 4. Let me write it out and show you. I was doing it in my head, that's why I got it wrong. So don't count me off yet. But I'm thinking where the error, I'm trying to see where the error is while I do this. This is 4, this is 16. You're welcome, I was real helping out. Should you just go with the large value, avoid the negative results? How do you determine which is the subtracted means? It's the B, it's B, because it uses y bar B minus y bar A. So it's the y bar B. It is the larger one for this problem always, but it's y bar B minus y bar A. So you use the mean for B, which is 53 right there. And so that should be square root of 1, which is square root of 1 is 1. And then we times that by this, which is 2.052. Hopefully I haven't made an error here. I'm wondering if it doesn't like the t for some reason. So we copy this. And then 53 minus 50 is this. So wait a minute, what happened there? So 3 plus 2.052 is that. And 3 minus it is this. So what went wrong? And I had a theory about it. Let me see something really quick right here with the degrees of freedom. Well, that doesn't change it nearly much. What is going on? So I've done this problem probably 50 times. Let's see. Oh my gosh. Somebody correct me. Somebody correct me. Somebody correct me. I know what it is. I'm not wrong. I don't think I'm wrong. I still don't think I'm wrong. Someone correct me. I would give you your points back if you did this. Yeah, I know, right? Don't do that. So I did it right. I did it in my head because the reason I was able to do it in my head is because the numbers were so they were nice numbers, because this was square root of 1, which square root of 1 is 1. That was so helpful. You're welcome. Awesome, Elias. See, I just get stuff wrong to show you guys. It happens. That's why I do it, you know? I was like, when you get something wrong, you're like, what did I do wrong? And you're like, it's the right interval. It's just the numbers are reversed. So it was the right interval. The numbers were just reversed. I'm so glad that helped you out, Elias. Swing by anytime. I think we have time. Check out the video I put in the chat. I might head off here in a moment. I'm trying to see if there's any other questions I can do kind of quickly because I have a noon meeting with TAs about grading projects. I'll tell them to be super nice. So I'll be like, you guys, be as nice as possible with the project. I probably will literally be saying that. Like, not as nice as possible, but try to give points, try to put good comments, let students know, makes it easier on us. Yes, I'll tell them, Trace, I'll be like, they think you guys are the best. So that's where I'm going in about 3-4 minutes. That would be wonderful. You're welcome. And so, Elias, I'm really glad that helped, just knowing the steps to do this question. And then just make sure to put your numbers in the correct order. Put the low number first. And don't do what Brian did. Tell them to boost John, all Johns. Say all Johns get grade boosts. So John's the lucky name right there. I think that might do it. Yeah, I'll probably hop on here a little bit later. Maybe, so expect me on around, maybe around 2:15. What applet do we use when we need 4 decimal places per p? Great question right there. And sorry, there's only like one question that needs that. And so sorry that exists. So that is the Iowa T applet. And so if you need supreme decimal place accuracy, Courtney, great question. Use this applet right here. It's only like one question that does that. So if I were to do, let me show you the applet right here. If I were to go here and I were to take my degrees of freedom, let's go grab our degrees of freedom. So here's the degrees of freedom. And I were to construct a 95% confidence interval in this applet right here, I'd have to go to the between numbers on it. And I think that's the outside actually. Oh no, it's the between. So now this one gives me 4 decimal place accuracy on it. And there's just like one Mike Pearson question. Once again, if you're in my class, please tell me if you missed something by, and see you, Tracy. If you missed something by like a decimal like this, if you enter in 2.05 and it's like, no, it's 2.0486, just tell me and I'll fix it. Can you do a question where it asks for T and P value? We probably don't have enough time, Barbara. Swing back by, I'll probably be on around 2:15 or so. So swing back by and ask for that specific question. If you just copy the start of it, I'll be on for maybe about an hour, probably about an hour, as long as people are here. Like if I come on, don't worry, like it gets boring for me. I've done some streams where I've kind of talked to myself and done a problem or two, but it's more fun when you guys are here and ask questions and you say, hey, do this question. And then it's been 2 hours and it just goes by like just quickly, just 2 hours fly by. So it's easier on me when you guys are here, and I like it because then I actually get to talk to people and answer questions. So I think that does it. We're going to take the advice of Rick Sanchez right here about the project. So let's hop in and hear some Rick Sanchez advice real quick again. So I will see everyone probably later today. Let's do it. You're welcome, Sarah. Good to help. And here's Rick Sanchez to end the class.
Morty, we've got to turn the project in early.